All right, thank you very much, Maddie, and welcome everyone to today's industrial webinar. This is the fourth and final industrial program webinar for Energy Star that we have this year, and I'm very excited for this topic. As Maddie said, if you're just coming in, please take a moment to answer our polling questions, which can be found on the right side. Maddie, did you see my slide move?
Yes, I did.
Okay, perfect. I'm in control. So again, welcome. Today's webinar, we're going to be talking about when electrification makes sense in manufacturing plants. We know that electrification is a pathway to decarbonization, and we're going to hear from two of our partners who will talk about how they assess when it makes sense and when it's viable. But first, just a few short announcements. I know some folks on this call, a lot of your plants are eligible for Energy Star certification. Just remember to submit those applications to me by December 15th. And if you aren't aware of what Energy Star certification is, if you have any manufacturing plants that fall into one of, I believe, 21 categories on the left, you may be eligible to put the Energy Star decal on your plant. You need to use our energy performance indicators to figure that out. Visit energystar.gov/plants to learn more. And you can always send me an email as well. Speaking of certification, 2 weeks ago, we were very excited to announce the first set of Energy Star certified distilleries. We've been working with the industry, with the Distilled Spirits Council of the US. We've been working with that group for over 2 years on developing an EPI to identify distilleries that are the most energy efficient in the country. And within a month of putting that out, we had 8 distilleries certify, and those are listed over here. I would like to congratulate any of them that are on the call. And yep, thank you for the hands. And if you are looking for a beverage that was made energy efficiently, you can consult this list. Okay, now for the main event of the webinar. So I think most folks are familiar with electrification, but just to make sure we have a baseline, when we talk about electrification, we're talking about the process of replacing technologies that traditionally use fossil fuels with technologies or processes that are electrically powered. So why there are some processes that have been commonly powered by electricity, when we talk about electrification, we're talking about replacing the ones that were traditionally fired by fuel with ones that are now electrically powered. And when you say you're electrifying, it does not always mean that you are reducing your emissions. It's really going to depend on the efficiency of the technology you're installing and the intensity of the grid. So when we refer to beneficial electrification, this is when you're powering traditionally fossil fuel technologies with renewable energy sources, whether that's from any on-site installations or purchase agreements. So again, electrification, I think we all recognize as a pathway for decarbonization, but it may not always be technologically possible or financially feasible. So recognizing that, what do you do? And I'm really excited for the two presentations today. We have JT Huffnagel, who is the operations manager of Corning's Global Energy Management Department, and Joe Swindler, who's a corporate energy manager for Honda Development and Manufacturing of America. And both of these companies have decarbonization goals, and electrification is part of it. And they are going to share with you what they did to determine when and where electrification made sense in their plants. Before I turn it over to them, I just want to invite people, if you haven't completed the poll, just take a few seconds to do so on the side, because we're going to get an idea of how far some of your companies have gone with electrification. So we'll give it about another 5 seconds or so, and then we'll show the results. All right, so Maddie, why don't we show the first one? Right, I'm actually having trouble. Oh, here we go.
Did
You
the
know,
results
I
look
am
good?
having trouble seeing the results. Would you mind reading them off, Maddie?
Yeah. So, let's see. It looks like I think most people had projects for the first question. Had projects that are being scoped. Um, with others choosing C and D. Not that many folks had chose A.
Okay, so not many folks may have had projects that that have been implemented, but they are starting to scope it and to plan it. And then the second question had to do with whether any of your utilities have provided assistance with electrification. Just fill that in, and it's good for us to know for future webinars. So what I would recommend, how can this webinar help you? Think about whether the approaches taken by these two companies can be replicated in your company. You may not have the same technologies and processes as them, but the point of this webinar is for you to really understand the process by which these companies are determining whether electrification is feasible. All right, I'm going to hand this over now to JT Huffnagel from Corning to talk about what they're doing. JT?
Very good. Thank you, Danny and Energy Star for having me today. Looking forward to the chat. So today I'm going to talk about a project that we launched at Corning called Natural Gas to Electrification, or because we have to put an acronym to it, NG2ECM. There we go. And so just briefly, a little bit about Corning. So we're a material science company. I've been around for over 170 years with a expertise in glass science, ceramic science, and optical physics. And we make products that all of us use that really on a daily basis that really enhance industry and people's lives. We sit in a small town in upstate New York called Corning. Closing in on $15 billion in sales, and a Fortune 500 company. We have 5 different business segments. The first one is our display technology business, which produces high quality glass substrates for LCDs and advanced displays that are used in TVs, monitors, tablets, and mobile devices. Our optical communication segment provides comprehensive range of connectivity solutions that provide fast, reliable broadband, linking businesses, data centers, homes, and people. Our environmental technologies business provides emissions control products for cars and trucks and off-road equipment, things like the filters and substrates that go in those catalytic converters. We have a specialty materials business that services a diverse range of industries from semiconductors to aerospace. And finally, life sciences business that has been a trusted supplier in the healthcare and pharmaceutical industry since Pyrex glass was introduced in 1915. And we provide today a broad portfolio of projects from labware to cell culture projects. So we do use a lot of energy, especially in our glass melting business and our ceramic fired business as well. And in both those businesses, especially use a lot of natural gas. So, why am I here today talking about this? Well, in 2021, Corning announced that we committed to Scope 1 and Scope 2 greenhouse gas emissions goals, aligning with the Science-Based Target Initiative. And we committed to a 30% absolute reduction of those greenhouse gas goals, of which 25% of our emissions come from Scope 1, the natural gas, essentially, and 75% come from Scope 2. Now, I think all of us probably know that it's a lot easier to address Scope 2 emissions through energy efficiency and renewable energy projects. But what about the rest of it, the 25%? How would we go about reducing emissions within our scope one? But high level, our energy reduction strategy within my department here of global energy management at Corning, this is sort of the approach that we take. First of all, we look to reduce energy waste. We work closely with our sites to do things like energy treasure hunts to identify those areas of waste that happen every day on plant floors. We use Energy Star modeling or guidelines and best practices to implement energy efficiency throughout our global organization. After those two, then we start looking at electrification. Where does it make sense to eliminate natural gas and to electrify our projects? And then, finally, can it be beneficial electrification, like Danny mentioned, tying that electrification to renewable energy, ensuring that we have enough renewable energy to cover the transition from natural gas to electric to really reduce those greenhouse gas emissions. So that word electrification, it's been so prevalent out there. And that tied with our 30% goal, our leadership asked us, okay, what would it take to electrify all of our plants? And then also we have to think about, okay, so we have this goal that extends to 2028. What's beyond that? We don't have anything targeted yet, but what would be beyond that? Would it be something another 30%, let's say, or would it be, I don't know. So we're trying to think a little bit long term. So the first thing that we had to do is identify opportunities and processes that are suitable for electrification. Sort of thinking a little bit more short term. And then, are there opportunities to replace equipment with electric equipment where feasible? There's equipment has, 15, 20, 30-year life. When does it make sense to replace those pieces of equipment? Third, how do we foster our innovation? We have a really strong R&D program here at Corning. How do we think about using innovation to move away from fossil fuels, as well as not just electrification moving away, but other low carbon fuels such as renewable natural gas or green hydrogen. So to get to the short, medium term, and long term solutions, we came up with simply the idea: let's go out to our plants and follow the pipe. So that's sort of how I think about this process that we have. So this project NG2 ECM, the objectives were to develop a clear understanding of where natural gas and how natural gas is utilized within our facilities. Second, we wanted to have a standard set of a standard way to go out and identify, inventory, and evaluate the opportunities in a global portfolio of plants and different type of processes, and then have a standard toolkit that would have to quantify, assess, and rank the different opportunities as well. So we didn't develop this internally. We used a consultant to help us develop this and create this, the tool, and also to train our folks as well. Some select folks within each division to go out and utilize the tool after we did a few of these projects, from a corporate standpoint. So basically, our implementation process looks like this. So there's pre-work on the front side. So we had the standard RFI, that we went to the plants and said, okay, this is the type of information we need to come on site and fill out this assessment tool. Such as the size of the facilities, the location, because we need the emissions, grid factors, what, how much energy is used at the facility, process flow, flow diagrams, the weighted cost of capital. And then on site, it was real important to have plant management involved, right? Have their buy-in actually beforehand too, not just the day to get have them be part of this kickoff meeting and part of the process on site, but get their buy-in ahead of time. Let them know why we're there, what we're doing, and the purpose of it, how it could benefit them in the future. And then key facility personnel lined up, key process people lined up, being able to access nameplate data, identifying what kind of metering is available for the natural gas lines. Is there a building management system data that we can access? So having all the kind of information available on site, but known ahead of time, knowing that we're going to need it, was real important to these assessments that took about 2 to 2.5 days. Next, we'd analyze our findings, document all the measures. So what we did in the assessment, just to be clear, is every piece of equipment that burned natural gas, we logged. And I'm going to at the end show sort of a live demo of the tool and what we did. And then for each within the findings to the analyze phase, so we have a air handling unit that burns natural gas. What's the electrification replacement? So that's in the tool as well. And then the post-assessment report, making sure that we're sharing this information with the right leadership in manufacturing, corporate manufacturing, plant manufacturing, the corporate energy management programs, corporate sustainability program, making sure we're sharing this information. So each one of the pieces of equipment that we identified, we decided to just categorize them in 3 different buckets, if you will. One, the short-term solutions, or what we call plant solutions, where there's already technology readily available to go out and convert. So simple things like hot water tanks, boilers, if money wasn't an issue, you could go out and swap those things out right away. Then there's what we call engineering solutions or medium-term solutions, where it's probably a piece of process equipment that there is an electric version available, but for whatever reason, probably operational costs, we just went with the natural gas version, but yes, that technology is available, and all in all, economically viable. So those first 2, there's a solution for. And then there's assets in the plant too, right, where we would have no idea on how to electrify, right? So we identify those anyway, and then we can give that information to the R&D community, as they think about sort of those long-term solutions to this problem. So over the last 1.5 years or so, we did 7 assessments. I mentioned Corning's 5 different business segments. We tried to get at least to each of the business segments to understand the different processes that use natural gas, in each of our different types of organizations. We found that there was tremendous support from the plants and from the facilities personnel. There's all the talk about sustainability and greenhouse gas reduction in the news, as well as from customers as well. We got people pretty excited about this, and we're encouraged. It also allowed us to sort of align resources, identify opportunities. Are there quick wins, right? To go ahead and swap out. Helped us with our CapEx planning. You know, we have a corporate capital expenditure program. You know, we're also using this as part of that process as we're identifying larger capital investments. We sort of built this into that program. So when we're, you know, expanding or building new plants, asking that question, can we use electric instead of natural gas for some of this equipment? You know, this also allows the R&D organization to prioritize where they may want to spend their dollars when they're looking at decarbonization opportunities. Which one of those businesses would be maybe a better fit to spend dollars on? And then it also helps us with our overall greenhouse gas strategy in our science-based target initiatives as well. So when we think about you know, our scope 1 and scope 2 reduction path, you know, is it all going to be through virtual power purchase agreements and green tariffs, or how does natural gas play into this as well? So those are some of the impacts that we've identified through this project. And just a couple snapshots here of other reports. So, you know, one of the things that when we look at all the equipment and the overall plant utilities, you know, what's the overall electricity consumption? What's the gas consumption? And then what's in orange there, the carbon intensity per the unit of production that we make at that plant. Sort of as of today, then after the assessment on the right-hand side of the bar graph, what would it look like if we were able to electrify all the items that we identified would be worth electrifying? So it shows that potential change there. And then the pie graph would just sort of break down where gas is consumed by sort of type of equipment. So just sort of a nice visual there. And then, you know, a couple others, you know, with electrification comes, you know, potential constraints on the plant's electrical capacity. So understanding where that capacity is, current state. And then if we were to electrify, what kind of, you know, would it push you up against your capacity? And this scenario would say, yeah, if we electrified, we'd be well above our electrical capacity at this location and would have additional investment in upgrading that system as well. And then, you know, one of the other outputs is a marginal base and cost curve. So I just put an example of what that is here that shows, you know, each one of those boxes represent a emissions reduction opportunity, where the x-axis is the emissions reduction potential for that individual opportunity, where the y-axis would be sort of the cost per ton of emissions, and then it's sort of left to right. So left, your most advantageous projects to go after versus the most expensive projects on the right-hand side.
Good afternoon, everyone. I'm Joe Swindler from Honda Development and Manufacturing of America. I'm an energy manager for them. Next slide. I wanted to talk about our process of deciding how heat pumps could help decarbonize at Honda. Just a quick review of how heat pumps work. The evaporator, as you can see in this picture with the blue lines, absorbs heat from the inside the building, and that heat is transferred to outside the building in the condenser and is rejected and then the whole cycle is repeated with the compressor turning the refrigerant gas from a low pressure to a high pressure, and the cooling of the refrigerant puts it back in liquid form. On the other hand, for heating using a heat pump, there's a reversing valve, and the heat of compression is dumped into the plant, and that heat heats up the interior of the building. And so that's your differences. Ambient is you determining which cooling or heating, the decision or which mode is in is based on rejecting the heat to ambient for cooling or rejecting the heat inside for heating. Next slide. So Honda looked at hydrogen-fired boilers. This was our first step for trying to decarbonize. And we have three 16 MMBTU gas-fired boilers at East Liberty. So we looked at our East Liberty plant in Ohio first for decarbonizing, since they have a central hot water system. Next slide. So we didn't know much about hydrogen and hydrogen-fired boilers. So we hired an engineering firm to do the analysis for us, and they broke it down into 3 phases. The first phase would be replacing one gas-fired boiler, and then the second will be 2 and 3. And you can see the peak MMBH there, they calculated for us, and how much natural gas in million BTUs we would need to replace our gas-fired boilers with hydrogen-fired boilers. This is for the East Liberty plant only. Next slide. What made it attractive at the beginning was possibly getting DOE grants to help pay for the new hydrogen-fired boilers. And also, the most expensive part was buying electrolyzers and making hydrogen on site. These particular boilers use both hydrogen and oxygen to produce 180-degree water. So what you see in there is just some DOE grants and how much the grant money was available in 2023. We did not apply for any of the grants, but this is what made the use of hydrogen-fired boilers attractive to us. Next slide. Hydrogen is being used for heating in Europe, and however, it's not, hydrogen infrastructure is not fully developed in the US. It has been started, but it's not fully developed, as you can see from this slide here. The bigger the dots, the more hydrogen is being used in that specific area. Next slide. The current cost of hydrogen is a concern. It's about $11 per kilogram, according to the DOE. They have a program in place to make hydrogen, the use of hydrogen, more attractive. And the program is designed to drop the price of hydrogen down to $1 per kilogram. So there is also a tax credit. If you make green hydrogen on site, the Internal Revenue Administration will give you a tax credit of $3 per kilogram if you make green hydrogen on site, if you buy electrolyzer and make it on site. So as you can see, if the cost goes down to $1 and they give you a tax credit of $3 per kilogram, you can actually make money. So that's that's the DOE way of incentivizing the use of hydrogen. Next slide. Then we looked at water source heat pumps to provide heat. And that technology is basically a chill water generator running in reverse or using the heat from the condensing side of the chiller. However, even on the hottest days of the year, your leaving water temperature from the condenser is 110 degrees. In the Midwest, Ohio and Indiana, for example, 180-degree water is really needed to heat up the building interior for HVAC applications. So 110-degree water is really not feasible. It can be done. You have to have large heat exchangers, but that is very costly. So that was, as far as HVAC solutions, water source heat pumps was what we looked at first. Next slide. And we also looked at heat pumps, 5 to 25-ton heat pumps with electric backup heat. And here you can see some of the specs on some of the heat pumps we looked at. However, the problem is the heating in very, very cold days or cold ambient days, you need extra heat to heat your building. And the heating using electric strip heat, the HVAC engineers, we call it strip heat, but it's basically electric resistance heating. And bringing that additional power can be a very expensive deal. So that's the problem with standard heat pumps with electric backup. Next slide. So here's an example. This is a small heat pump. So as you can see, the coefficient of performance is shown there at 17 degrees and 47 degrees. That's what heat pumps are usually rated as far as heating, at 47 degrees F and 17 degrees Fahrenheit is standard for ASHRAE. And you can see the COP at 17 degrees is a little bit above 2, and the COP rises to around 3.5 at 47 degrees Fahrenheit. That's ambient temperatures. And you see that's a huge drop. So as it gets colder, the heat pump becomes less efficient at heating. And then you can see your heating capacity in BTU per hour in the blue line there. So, and as you can see from the graph there, once you get below 5 degrees, you're not going to get any heat out the heat pump. So electric resistance heating is needed. The efficiency of gas-fired burners range from, they're typically around 80%, but if you use heat recovery, heat exchangers, you can get all the way up to 95, 97%. And your electric heating can go up to like 99 to 100%. And keep in mind, efficiency and coefficient of performance, they are two different things. Theoretically, you can't have more than 100% efficiency. So COP was developed for chill water generators, for example, because you're using refrigerant to absorb heat and transfer heat. So you can get a better than 100% efficiency. So that explains the difference between efficiency and coefficient of performance. So again, your heat pumps are actually more efficient than your traditional forms of heating due to the COP. Next slide. So going back to the electric backup heat. So you can need as much as 30 kilowatts for this particular heat pump. Next slide. So just a typical example, just to give you a better idea of how much backup electric heat is needed. For a 15-ton heat pump in the Midwest, 72 kilowatts of electric backup heat is needed. And if you go up to Ontario, Canada, which we have a plant in Canada, you can need, where it gets much colder, you can need as much as 132 kilowatts of backup heat. And again, the problem with that is bringing that power to the heat pump as backup heat. So that's all that electric equipment. And then the operation, electricity is 5 times more expensive to use than natural gas. So you have increased operating costs, and then you have increased electrical installation costs to aggravate the situation. Next slide. So we are doing a trial in Canada at our HCM plant, we call it Honda Canada Manufacturing, with 5 to 25 ton heat pumps. What they decided to do was to keep the existing gas heating coil and purchase a heat pump, and they would use the heat pump to provide heat from 30 degrees ambient to 50-degree ambient temperatures. And then the heat pump would, the natural gas, they would keep the natural gas heating system under when ambient is 19 degrees and lower. So what it does is reduces your natural gas usage significantly between 50 degrees and 20 degrees. So there are dual fuel heat pumps out there, and heat pump is used to provide heat down to 20 degrees, for example, and then you turn on your natural gas fired burner to provide heat when it's 20 degrees or lower. Next slide. So I did some engineering analysis. We discovered that dual fuel heat pumps had a lower internal carbon price than standard heat pumps with electric backup. Again, the reason was because natural gas is cheaper to use than electricity. On an annual energy usage analysis, again, the internal carbon price is lower. The method I used was weather bin data. As you can see, the temperature ranges on the far left, and then the hours per year, the ambient temperature is expected, in this case, is in the Midwest. So I compared the two. Heating with a heat pump with natural gas backup, it reduced natural gas usage by 692 MCF per year. And then if you eliminate natural gas as backup when it's very cold, it reduces natural gas usage even more by 867 MCF per year. But so that's a large amount of natural gas. But as you can see with the dual fuel heat pump, you still have a very significant amount of natural gas reduction per year. So that's what the analysis showed us. You don't eliminate all the natural gas, but you eliminate about 80% of the natural gas usage. Everybody wants to decarbonize, 100%, but sometimes it gets very expensive. Next slide. So in summary, the plan at Honda, we plan to use heat pump for office areas and applications that require 5 to 25 tons of cooling. Just to give you a general idea, the equivalent heating demand for these applications would be 112 MBH up to 450 MBH. So the lower range is for the South and the higher range is for Canada. And our southernmost plant in the US is Lincoln, Alabama. Next slide. So we took a second look. So that's our strategy going forward. But for bigger applications, we took a second look at water source heat pumps. And what we decided to do there was, even though with the water source heat pump only making 110 degrees, we could use waste heat from air compressor, cooling water, RTO, flue gases, etc., to help, and some heat exchangers to help increase the temperature up to 180 degrees. So that's our plan going forward, is to use water source and air source heat pumps to make 180 degree water for larger applications. Next slide. So this is air source heat pumps. Again, the key will be providing waste heat on low ambient days in the Midwest to achieve the 180 degree water temperature. Next slide. In summary, Honda explored space heating alternatives as a result of requests from Honda headquarters in Japan. We looked at hydrogen-fired boilers, water source heat pumps, air source heat pumps for backup, and dual fuel heat pumps. Dual fuel heat pumps, which uses both natural gas and electricity, we decided that was the most appropriate option from 5 to 25 tons. Any questions?